Hello, this is part 2 of our analysis of churn using Keras and using an artificial neural network that we trained and developed using Azure machine learning. And in the first part 1 video, which is called Churn Keras Artificial Neural Network, what we did is to generate a data set with features from telecom company and feed that model, train it, and calculate how is this model working using the different metrics. So in this video, we're going to explain those metrics, how to evaluate a classification model, binary classification model in this scenario. And we will also try to identify if those metrics were good, were not good, and what other options we might have to increase the accuracy, precision, recall, and those metrics that indicates if the model is working fine or not. Imagine you're running a nightclub and you have a bouncer at the door. The bouncer is checking IDs for everybody that's coming in. What's a true positive? The bouncer correctly lets in people who are plus 18 years old. So party on, you can go in. What's a false positive? The bouncer lets in a 16 years old with a fake ID, but oops, he tricked the bouncer and he went in. False positive. What's a true negative? True negative is when the bouncer correctly rejects a 14-year-old. He sees he's not old enough. Good job, you cannot go in. And what's a false negative? The bouncer mistakenly rejects a 25 years old just because, just because he looks too young. I mean, not old enough. So imagine that's the example. Poor guy, he looks too young, but he actually could have entered the nightclub. So this analogy is very important to be identified in every classification machine learning problem. Now, what is rock and area under the curve? Well, it falls over. So if the bouncer is too strict, fewer underage kids will get in, so you have a low false positive, but some real party goers get turned away, high false negative. If the bouncer is too relaxed, everyone gets in, but now you've got minors drinking inside. So that's a high number of false positive. The rock curve shows how the bouncer balances this, adjusting how strict they are. For example, an area under the curve of 1, that means the bouncer would be perfect. No fake IDs get in. If, on the other hand, the area under the curve value is of 0.5, that, for example, means it's like flipping a coin, 50% chance of letting in, 50% chance of not. And below 0.5, it's absolutely worse than random. It would do everything upside down. A high area under the curve, closer to 1, means your model is good at spotting churners versus non-churners. Just like a smart bouncer can know who to let in. Just to provide a little bit of context, in a scenario like customers' churn prediction, if we are going to apply on our daily work, we maybe want to create marketing campaigns or allocate efforts to improve our products or services. So we would like to know which of the customers have a highest probability of leaving our company. If in our modeling prediction, we find a customer that we think, based on the results of the model, is going to churn or to leave our company, but actually is not going to leave, that kind of errors, what would be called a false positive, in this scenario is not too dramatic, it will maybe generate some confusion or especially waste of cost and efforts of doing a campaign to a customer which is not uh, in the area of leaving the company. But in the other side, if we have, for example, true positives, so we will predict which ones are going to go to do churn, or if we have, for example, false negatives, customers that our model labels them at not doing churn, but then in the end they do churn, that could be a bit of a problem because we are going to lose the target of this whole model, which is to reinforce the marketing actions and the customer satisfaction actions for those customers. Here we have our notebook. As you can see, we have calculated the in-sample and out-of-sample accuracy, precision, and recall. And the results, you can see them, 0.8, 0.78 for accuracy, both the same, no overfitting. What we have, we also have ROC, receiver operation curve, area under the curve. We are going to calculate it, and we have an in sample of 0.9 and out of sample 0.8, close to 1, almost perfect. Good. That sounds quite good. The only thing that it's not very good, maybe, as we have seen, is recall before for out of sample, which we have only 0.4. So what are we actually meaning here? We're going to plot the rock curve and you're going to see the area under the curve. The straight line that we have would be 0.5 for area under the curve. But as you see, in sample and out of sample curves are quite close to the left top corner, which means they are discriminating quite good with a very good accuracy the real churners from the not real churners. So our model has been trained in a quite a good way. Yes. Well, first of all, I will provide a quick definition of some terms, but there are some scenarios in which accuracy, precision, or recall might be most important or least important metric to optimize. For example, where accuracy is key. In a disease diagnosis, in routine checkups, for example. A general medical test is used for routine health screening, for example, annual checkups. Accuracy is good because false positives and false negatives are both undesirable. So we want a balanced model that correctly classifies both healthy and sick patients. Since diseases may be rare in general population, we don't want an overly sensitive model that flags too many false alarms. In this scenario, it's very similar for our customer churn. We want a balance and not to lose too much effort and not to, of course, lose any possible candidate to churn. Where precision is more important, for example, in fraud detection in banking. Imagine a bank that uses an artificial intelligence system to detect fraudulent transactions. Precision is key because false positive flagging legitimate transactions as fraud are very costly because the inconvenience that those customers can get, and that can, of course, lead to a lot of trust lost, which is horrible for a bank. So it is more acceptable to occasionally miss a possible fraudulent transaction, a false negative, than to constantly block legitimate transactions. A bank wants to ensure that flagged transactions are almost always truly fraudulent before acting on them. Or, for example, if we are going to use artificial intelligence to provide cancer detection, their recall is the most important metric. A model, for example, that uses computer vision from X-rays to detect cancer, if we are missing a true cancer case, which would be a false negative, it's much worse acceptable to have some false positives, as this can be ruled out with further medical testing, but missing a true case could be fatal. A cancer screening tool where detecting all possible cancer is the priority, even if it means some extra testing for false alarms. Well, there are in-sample accuracy, which we have in-sample accuracy of 0.84, out of sample accuracy of 0.78, in sample precision 0.73, out sample precision 0.62, in sample recall 0.61, out sample recall 0.478. So if we have in sample accuracy of 0.8, out sample accuracy of 0.78, in sample precision of 0.73, out of sample precision. Well, in sample and out of sample means if we are using the data that has been used for training the model, or if we are calculating the metric on the data that has been used to test the model. So of course, it's normal that the data that has been used to test the model, it's a bit lower on the predictions. You can say from our example, what is clear is the following. We do have a slightly drop in the accuracy. So the small drops, it's just a 2% from 0.8 to 0.78 for accuracy. That suggests that we don't have a lot of overfitting, which is good. That makes the model more expandable for new data. There is a drop in precision from 0.7 to 0.6. Precision is how many churn cases were actually churners. So that drop means that the model is making more false positives than we would like. For example, predicting churn where the customer didn't churn. It's not the most serious thing that could happen, but of course, we are going to lose efforts on retention for non-churners. But then we have a significant drop in recall. Recall, it's true positive divided by the number of true positive plus false negatives. So how many actual churners were correctly predicted? A drop from 71% to 42% means the model is missing a lot of real churners, more false negatives. The company in this case will fail to identify 58% of churners, leading to lost customers who could have been saved. To decrease a bit the precision and just look forward to increase recall. So even if we identify as churn a customer that would not have churn, it's better to catch exactly the more churners as possible. That's why there are techniques like, for example, we could modify the threshold or the classification rate. Instead of 0.5, 0.4, we could use regularization techniques and others, but we have to
increase recall to go and add oral actions, marketing actions to retain those customers that we don't want to lose.
These numbers, of course, can be improved. We can say that the model is failing to detect some of the churners with real-world data. It's clear that we have to add more relevant features, not only the ones that we have used to predict churn, probably adding some feedback from customer satisfaction, maybe number of issues that they have happened with the service would have helped to identify this churn, because we were only based on their demographics and what services they had. So a feature engineering can be very important and relevant. Also, we can apply regularization, we can apply class weighting, because maybe the classes are imbalanced. We have to study if each of the features are correspondent to the balance of classes. Maybe we can adjust the model by using decision trees, learning rates, and other hyperparameters. And well, we can add an adjustment of the threshold to balance precision and recall based on other business needs. We've used a neural network, but maybe if we would have used a random forest or XGBoost, for example, we could have had better results. So as another exercise, we will do it in later videos.
Well, thank you very much for having seen this video. Hope you find some time to practice. And well, don't hesitate to contact me and follow me for any other content regarding artificial intelligence in data science. Cheers.